And I'm going to project my screen so that you all can follow along with me. Okay, can you guys see my screen?
Yeah.
Okay. All right, you guys, so let's just get started. I want to first, the mole is probably the most important topic that you can learn in chemistry because it's the basis for so many other things that you'll do. And don't get confused about the word mole. A lot of kids are like, what's a mole? Is that a rodent? And it's not a rodent. It's just a counting word, kind of like dozen. What does the word dozen mean, you guys?
12.
12. A ream?
500.
500. A gross is 144. Those are all counting words. In chemistry, we need a big counting word because if I have a sample of a chemical, there's not 12 or 500 or 144 atoms in there or molecules in there. There's millions and millions and millions. And so we need to use a counting word that means a lot more than 12 or 500 or 144. So in chemistry, the counting word that we use is the mole. And the word mole actually means 6.02 times 10 to the 23rd. So that is a really big number. And what that number actually is, if I were to take that decimal and move it to the right 23 times, and then put zeros in all those spots, and you guys get the drift, that is a really, really big counting word. But that's what we use in chemistry because we're counting really, really small things, okay? So if I have a mole of books, how many books do I have? 6.02 times 10 to the 23rd. If I have a mole of donuts, how many donuts do I have?
6.02 times 10 to the 23rd.
Yep. If I have a mole of dogs, how many dogs do I have? Hi, Lubomir. So if I have a mole of dogs, how many dogs do I have? And you guys can all, there's not a lot of kids in this, so you can all take yourself off of mute and then just answer questions as I ask them, okay? So if I have a mole of dogs, how many dogs do I have?
6.02 times 10 to the 23rd.
Yeah. Okay. So that's all a mole is. Like a dozen is 12, a mole is 6.02 times 10 to the 23rd. That number, you're often going to see that referred to as Avogadro's number, and it's named after the gentleman who related the count of atoms to their volume. So I'm going to use this number to count things in chemistry. But so what are we actually counting when we use that number? We're counting something called a representative particle. And a representative particle, a lot of times you'll see me abbreviate that as RP. And a representative particle is just the smallest piece of a substance that still retains the properties of that substance. So for example, if I have an element like iron, if I have a sample of iron, I'm going to count iron atoms. So I'm going to use Avogadro's number to count atoms if we're talking about an element. For a compound, we're going to count one of two things. If I have a compound and it's ionic, we call the things we're counting, the smallest piece that we're counting, we call it a formula unit. So for example, if I have a sample of sodium chloride, a formula unit of sodium chloride would be 1 NaCl. We call that a formula unit because it's an ionic compound. Now, if I have a covalent compound, we count molecules. So for example, if I have a sample of water, here's my collection of water molecules, one water molecule would be called a molecule. That's what we'd be counting. So we could count formula units or molecules for compounds, and we can also count ions. So if ever you are doing a conversion where you have to get a count of atoms, a count of formula units, or a count of molecules, you're going to be using Avogadro's number. By the way, for ionic compounds, we are going to abbreviate that as Fu, okay? I know that's funny, but that's just the way that we're going to do it. Just so you don't have to write that whole thing out, okay? Do you guys have any questions about what a representative particle is?
No.
No.
Okay. Okay. So like, for example, for an element, if I have a sample of iron, that sample of iron is going to be made of a whole bunch of iron atoms. One of those iron atoms would be a representative particle of iron. Okay. And that's what we would be counting with Avogadro's number. So how many atoms are there in a sample? How many formula units are there in a sample? And how many molecules there are in a sample? We can also count ions. Now, can we actually look, if I have a sample of sodium chloride, can I look with my bare eye and see how many formula units are in that sample? Would that be possible?
No.
No, it's not. So because that's not possible, because we can't see something so small, we have to be able to convert that count into something that we can measure in the laboratory. And the two things that we can measure in the laboratory is mass. I could put it on a balance and I could mass it in grams, or I could use a graduated cylinder or beaker and I could figure out how many milliliters it is or how many liters it is. And that's why we're doing these conversions. If I have a sample of, let's say, sodium chloride in the laboratory and I know how many grams it is, I can actually do a calculation to figure out how many formula units are in that sample. Or if I have a sample of water and I know how many milliliters it is, I can actually do a conversion and figure out how many actual H2O molecules are in that sample. And that's what we're doing here. Does that make sense, you guys?
Yeah.
Okay. All right. So let me just check the meeting to see who's here. Okay. So the first thing that I want to talk about is how do I relate the mole to mass? If I have a mass in grams, how do I figure out how many moles that is? If I have a mole count, how do I figure out how much mass that is? Does everybody have a periodic table in front of them?
Yeah.
Okay, because you're going to need it. So here's the beauty of the periodic table. So I'm going to look at the periodic table we normally use in class. Here's the beauty about the periodic table is that on this periodic table, these masses at the bottom, all those masses on the bottom are how many grams it would be if I have 1 mole of particles. So for example, let's take a look at carbon. If I have 1 mole of carbon, which is 6.02 times 10 to the 23rd carbon atoms, if I put that sample on a balance, it would have a mass of 12.0 gram or 0.01 grams. If I had 1 mole of nitrogen and I took that sample of nitrogen and I put it on a balance, it would have a mass of 14.01 grams. All of these are what we call molar masses. What if I had a mole of sodium? How many grams would that be?
22.99.
22.99. If I had a mole of fluorine, how many grams would that be?
19.
19. So we're going to use those molar masses to be able to relate the mole to a gram amount. Okay, so I have to teach you how to calculate a molar mass. So here's what we're going to do. So molar mass is the mass of 1 mole. If ever you're calculating molar mass, the unit that's going to be on that is going to be grams per mole. MOL is the abbreviation for mole, just so you guys know. So give me the molar mass of hydrogen. Stephanie, can you give me the molar mass of hydrogen, please?
1.01.
That's a naked number. What unit it should go on it?
AMU.
Not AMU. So if it's the molar mass, what
MOL.
grams per mol. It's how many grams there is per 1 mole. Okay? Does that make sense?
Yeah.
What about sodium? Lexi, can you give me the molar mass of sodium?
22.99 grams per mole.
Good. Okay. But a lot of times we're dealing with compounds or molecules that are made of more than one element. So the way that you find the molar mass of a substance that's made of more than one element is you just look up their molar masses, figure out how many atoms there are of each atom, and then add them all together. So what I mean by that is this. Let's take a look at CO2. The first thing that you're going to do to calculate the molar mass of CO2 is we're going to take an inventory of what types of atoms are here. So we've got carbon, and we've also got oxygen. I like to draw a line there. You don't have to, but I like to draw a line there just because that's how my brain organizes itself. And then I want to take a count of how many atoms of each of those I have. So there's an imaginary 1 here if there's nothing written. So how many carbons do I have?
1.
1. And we're going to multiply that by its molar mass. What's the molar mass of carbon?
12.01.
Yep. And then we're going to do the same thing for oxygen. How many oxygens do I have here? It's the subscript on that element.
2.
2. And we multiply that by the molar mass of oxygen, which is 16. Okay. Do you guys know where I'm getting those numbers from?
Yeah.
Okay. So then multiply them together. This will be 32. And then you add. So 32 plus 12.01. You guys have calculators out?
Yeah.
Can someone do that math for me, please?
44.01
What unit should be on there?
grams per mole.
Grams per mole. Okay. Now, if I have something like this, where I have parentheses, you're going to split up this polyatomic ion into its individual atoms. So I'm going to go, I have calcium, I've got phosphorus, and I've got oxygen. How many calciums do I have here?
3.
3. How many phosphorus do I have here? If there's parentheses around a poly and there's a number on the outside, you distribute that to all the subscripts inside the parentheses. So we're going to multiply. So 2 times 1 is
2.
2. And then 2 times 4 is
8.
8. A lot of kids want to take this 2 and put it on the calcium as well, but that 2 only goes to what's inside the parentheses. So then we look up the molar masses on the periodic table. It's the molar mass of calcium.
40.08.
Okay. What's 3 times 40.08?
120.24.
120.24. And then 2 times the molar mass of phosphorus. What's phosphorus, you guys, so I can write it down?
It's 30.97.
Okay. So 2 times 30.97.
61.94.
Okay. And then oxygen is 16. So 8 times 16 is
128.
okay. So once you have all those numbers, you're going to add them together. And you always want your molar masses to the hundredths place, so to the decimal. So 128 plus 1.94 plus 120.24.
310.18.
Is that what you guys get to? Class consensus?
Yeah.
Yeah.
Okay. Okay. So that's how we calculate the molar mass. Are you guys good with that?
Yeah.
Mm-hmm.
Okay. Now, I want you to realize that we can use this as a conversion factor because this is the same thing as saying 310.18 grams is equal to 1 mole. So if I had 1 mole of this calcium phosphate, it would have a mass of 310.18 grams. So we're going to exploit this and we're going to use this as a conversion factor to do our conversions in chemistry. So we've established 2 different conversions. We have 1 mole is equal to 6.02 times 10 to the 23rd representative particles. And remember, the representative particles we can measure are molecules, formula units, and those are the most common ones, and atoms. But we can also measure or count ions, but that's a less common one that you'll see. And then if I have, I can also use 1 mole is equal to our molar mass in grams. I want you to realize that what number is always with the word mole?
1.
1. So there should never, ever be any confusion as to what number we put with the mole, because you're always going to put the number 1 with the mole. Always, always, always. So for example, if I have a problem like this that says, given 6 moles of CH4, how many molecules are present? Now, what I always like to do is you always need to know where you're starting in the problem and what you're trying to get to. You always start with the number, the unit, and the substance that's given. Really try to get in the habit of writing the substance in 2, because that's going to be important later. So I'm starting in moles, and they're asking me to convert to molecules. You're always going to write down the number, the unit, and the substance that they're giving you. So I'm starting with 6 moles of CH4. Now we're going to go up here and we're going to say which one of these 2 equalities will get me out of moles and into molecules. We'll take a look. Molecules is right here, right? So if I want to count molecules, I have to use the equality 1 mole is equal to Avogadro's number. Now, as always, like you guys saw with the unit analysis lesson, if I have moles on top, you need moles on the bottom so that it cancels out. So like I said, kitty corners cancel. So if I have moles on top in my first step, I know that I need moles on the bottom and I need molecules on top. So let's go to my conversion. 1 mole is equal to 6.02 times 10 to the 23rd molecules. Moles cancel out. I'm left with molecules in the upper right. So if everything cancels out top to bottom, because when you take something, you divide it by itself, it turns into 1. So if I have a mole on the top and a mole on the bottom, it cancels out. I'm left with molecules, which is what they're asking for. So you know you've done your problem right. Now, the hardest part that kids have with this is actually putting Avogadro's number into their calculator. Did you guys watch Mrs. Minton's screencast and how to do that?
Yeah.
Okay. Do you have any questions about putting Avogadro's number into your calculator? Could you all find your EXP or your EE button?
Yeah.
Yeah.
Right, you're good with that?
Yeah.
Mhm.
Okay. All right. So when you do this thing, could you guys calculate it and see if you can get the right answer? Shiloh, no. Shiloh, no. No. So this is what I got. I want to make sure that you are able to get this as well. Now, unfortunately, we don't have time to show you how to round properly. So just round to the 100th place for now. You'll learn how to round when you take AP. So this is the answer that I got. It's 3.61 times 10 to the 24th molecules. Were you guys able to get that answer?
Yeah.
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 Okay. All right, so let's do the next example. So it says, if you have 3.7 times 10 to the 22nd molecules of water, how many moles of water do you have? So again, we're going to figure out what we're starting with and what they're asking for. I have 3.7 times 10 to the 22nd molecules. And what are they asking you to find?
Moles.
Moles. Always start with the number, the unit, and the substance that they're giving you. So I'm starting with 3.7 times 10 to the 22nd molecules of water. And I want you guys to realize that this number is really big. And whenever we're talking about the particle count, that number will always be really big, because if I have a sample of something in the lab, there's millions of particles in that sample. So, all right, so now I have to relate molecules to moles. So which one of these equalities will I use if I want to relate molecules to moles? The top one or the bottom one?
The top, right?
Top.
To be, because there's mole, there's molecule. So I have to use that top one. Yes. So but this time, because I have molecules on the top, I need molecules on the bottom. And I need to put 1 mole on the top. So I'm going to go 1 mole over 6.02 times 10 to the 23rd molecules. Now, molecules cancel. I'm left with moles, which is what they're asking for. You multiply the numbers across the top and then hit your equal sign and then divide by the numbers on the bottom. So I'm going to go 3.7 times 10 to the 22nd divided by 6.02 times 10 to the 23rd. Can you guys please do that one and then see if you get that answer? Were you guys able to get this answer?
Yeah.
Yeah.
Okay, if you're not, you're doing something wrong with your calculator, make sure you tell me so I can fix it for you. So you guys are all able to get this?
Yep.
Yeah.
Okay. Okay, so now, example 3. Now we're going to use molar mass. Okay, so with this problem here, they're asking you, if you have 4.5 moles of sodium chloride, which is NaCl, how many grams do you have? So I want to go from moles to grams. So this is a mole to gram problem. So I'm going to start with the unit, or the number, the unit, and the substance. And I want to convert this to grams. Sometimes kids like to put a gram over here so that they can keep in mind as to what unit they're trying to find. So I want to go from moles to grams. So they're going to go up to our bag of tricks. So we're going to go up to these equalities. This is 2 of the 3 equalities you're going to have to use. So there's only 3 equalities you're ever going to have to use for these. You're going to go up here and you're going to say, which one of these 2 equalities shows me a relation between moles and grams?
The bottom.
Mole with molar mass of the substance in grams. So molar mass of what though? What molar mass am I going to have to find here?
Sodium chloride.
The sodium chloride, because that's who we're talking about. So then we're going to have to find the molar mass of sodium chloride. This one is easy because I just have one of each. All you have to do is go to your periodic table, find the molar mass of sodium, which is it 22.99 off the top of my head?
Yeah.
Yeah.
And chlorine is 35.45.
Yeah.
Yes.
Look at me go. And then you just add them together because there's just one of each. So what's the molar mass of sodium chloride?
58.44.
Okay. Now that's grams per mole, right? But realize that that also can be written as 58.44 grams per 1 mole. And that's the equality we're going to use here. So if I have moles on top, kids, what has to be on the bottom? Your choice is the 58.44 or the 1 mole. Which one is going to go on the bottom?
The 1.
It has to be because I need kitty corners to cancel. So that cancels out, and then I'm going to put the molar mass on the top. And if you have the unit you want in the upper right when you're done and everything else cancels out, you know you've done it right. Multiply across the top, divide by what's on the bottom. So 4.5 times. What do you get?
262.98.
I also get that number. Okay, grams of sodium chloride. So what that means is if I have 4.5 moles of sodium chloride, which is a lot of formula units, and I put that on a scale or a gram balance, it would have a mass of 262.98 grams. Okay. You guys with me so far?
Yeah.
Okay. So now there's one more equality that we can use. So Avogadro's says that if I have a gas at something called standard temperature and pressure, which is 1 atmosphere and 273 degrees Kelvin or 0 degrees Celsius. So if I have a gas and it has those conditions, it's at 1 atmosphere pressure and it's at 0 degrees Celsius, it's always going to take up 22.4 liters of space. So if I have a mole of a gas, it's going to take up this much space. And that's like, if you can imagine a 2 liter of pop, that's about 11 2 liters of pop. So here's one more equality that I can have, is that if I have 1 mole of gas, it's always going to take up 22.4 liters of space. If it's at standard temperature and pressure, which is 1 atmosphere and 0 degrees Celsius or 273 degrees Kelvin. And standard temperature and pressure, guys, is just something that scientists said, hey, when we do experiments so we can compare our data, let's make sure that we all do it at the same temperature and pressure. And that's 0 degrees Celsius, 1 atmosphere pressure. And I also want you to realize that if I ever have like hydrogen or nitrogen or oxygen or fluorine, chlorine, bromine, iodine, if you are ever using a diatomic molecule, remember that it's written as a diatomic molecule. And remember, the way that we remember it was Hunkelbrief. Do you guys remember that?
Yeah.
Okay. All right. So let's go ahead and do another conversion using this equality. So number 1 says, how many moles of hydrogen gas would be in a volume of 44.8 liters at standard temperature and pressure? So I'm starting with 44.8 liters, and I want to convert that to moles. So I'm going to go 44.8 liters, and I write my liters, guys, as a cursive L, just because my college chemistry professor did it, and also so that I don't confuse the unit liter with a 1. Because a lot of times when kids write liter, it kind of can be mistaken as a 1 sometimes, especially if you're writing a sloppy. So that's how I write my liter. And it's hydrogen gas. So remember, hydrogen gas is a diatomic molecule, so it's written as H2. Now, I want to convert that to moles. So ever you want to go from liters to moles, you're going to use this equality. So we're going to go 22.4 liters of hydrogen is 1 mole of hydrogen. Who can tell me why I chose to put the 22.4 liters on the bottom?
Because you have to cancel out the liters, basically.
Yep, because you got to cancel out the liters. I want to convert to moles, which is what I did. So then now all you have to do is do your math, because that's what they're asking for. So I go 44.8. Do I really need to multiply by 1?
No.
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 So 44.8 divided by 22.4.
2.
So this is going to be 2 moles. And if technically I'm using my rounding rules for chemistry, just if you're taking AP, I would write that as 2.00 moles. But you wouldn't know how to round. So if you wrote 2 moles, I would accept that at this point. So I want you to realize this makes sense, because if I have 22.4 liters, that is 1 mole. But realize 44.8 is double that. So doesn't it make sense that 44.8 liters would be 2 moles then? Yeah. Okay. All right, let's do another problem. This is a 2-stepper. So it says, how many grams of hydrogen gas would be in a volume of 44.8 liters at STP? So now I'm starting with 44.8 liters of hydrogen gas still. So I'm still talking about hydrogen. But now instead of going just to moles, I want to go to grams. Okay. Just to give you guys a hint, if it says the word mole in the problem, it's just a 1-step problem. If the word mole is not in the problem, it's going to be 2 steps, meaning because I have to go through the mole. So just to give you like a visual of what we're doing, so I'm starting in liters and they're asking me for grams. So to give you a visual of what we're doing, there's this mole chart that is on your worksheet. This is a beautiful thing. And normally when we teach this class traditionally, you don't get to use this. But I mean, since we're crisis teaching, you do, which is kind of great. So what we're doing here is this. We're going from volume, which is in liters, and we're going to grams. There's no direct relationship between liters and grams. There's no equality that directly relates liters to grams, but I can go from liters to moles, and then once I'm in moles, I can go from moles to mass. And they actually give you the equalities that you have to use here too. So the first step after I write down the number that's given is I'm going to use 1 mole over 22.4 liters. That gets me to the mole. And then the second step is going to be using the molar mass of the substance, which is going to be in grams over 1 mole. So this is a 2-step problem. For your representative particles, remember the things we're counting when we're using Avogadro's number, we're counting formula units, we're counting molecules, we're counting atoms, and sometimes we're going to count ions. So in this problem that I gave you, we're going to go from liters to moles and then moles to mass. Okay, so let's go ahead and do that. So my first step is get to the mole. And do you guys notice in do you see how it doesn't say the word mole anywhere in this problem? That's how you know it's a problem. Okay, we got to go through the mole. So the first thing we're going to do is we're going to use this equality first, because I got to get from liters to moles. So I'm going to go 22.4 liters of H2 is 1 mole of H2. I cancel out liters. Now at this point in the problem, I am in moles, but I have to keep going because they are asking for grams. So now in moles, I need to go from moles to grams. So now I have to use this second equality. I have to decide who's going to go on the top, who's going to go on the bottom. 1 mole is on the top, so guess who has to go on the bottom?
Mole.
1 mole, so they can cancel out. And now I have to find the molar mass of hydrogen and use that at the end. So what's the molar mass of hydrogen?
It'd be 2.02. That's its diatomic.
Correct. So we go 2.02 grams of H2, and then we just do our math, okay? Please do not split this up, because I saw a lot of kids on their homework stopping after this step right here, calculating it, and then doing the next step. Don't do that, because you're going to get wrong answers because you're rounding incorrectly. Just keep everything right in your calculator. So what you're going to do is you're going to go 44.8. I don't need to multiply by 1, times 2.02. So multiply the numbers across the top. So 44.8 times 2.02, hit your equal sign. And then divide by the numbers on the bottom, divided by 22.4. What do you guys get?
4.04 grams of H2.
Let me just make sure. Class consensus.
Yeah, that's right.
4.04, yep. Okay. And that is how we do these conversions. I'm going to give you guys one to do by yourself, okay? And I want to see if you can get it right, and then we can be done. So what if I have, I'm just going to make up something, 2.57 grams of calcium carbonate. And I want to know how many formula units are in that sample. Okay. First of all, so I would say you have 2.57 grams of calcium chloride or calcium carbonate. How many formula units would be in that sample? First of all, would this be a 1-step problem or a 2-step problem?
2.
2.
How did you know?
There's no mole.
Yeah.
There's no mole. Yep. So you don't see the word mole. We're going through the mole. So this is going to be a two-step problem. Can you guys go ahead and solve this for me? Oh, hey, Maggie. So write in the chat and say done when you're done. So when you're done, write in the chat that you're done so I know.
So would your unit be like molecules?
No. Calcium carbonate is an ionic compound. So if we're measuring particles, if we're counting particles of an ionic compound, it would be in formula units.
Ah, okay.
Okay. Lexi, Stephanie, you guys doing okay?
Yeah.
Yeah, I don't know if I'm doing it right, but
Okay. Who said that, Stephanie or Lexi?
I did.
Who's I?
Stephanie.
Okay. I thought so. I thought I recognized your voice because I wasn't sure. Good, both my dogs are sleeping. That's a good thing. Lexi, Maggie, you guys ready?
yeah.
Okay.
I don't know what I'm ready for.
You what?
I don't know what's going on.
Oh, did you just come in?
Yeah.
Okay. Just to say hi?
Yeah, I guess. And to learn.
Okay. So if I have 2.57 grams of calcium carbonate, and that's what we're starting with, we have to go through the mole. So now in this one, if you guys use the mole map, we're starting in grams, which is here. And they're asking for representative particles, which is here. So our first step is going to be 1 mole over the molar mass. And then our second step is going to be Avogadro's number over 1 mole. You guys see how that works?
Yeah.
Okay, this is a beautiful thing. Like, since you guys can use this, I mean, if you're taking AP Chem next year, I would get in the habit of possibly trying to do it just by looking at the equalities, but this is a beautiful thing right here. Like, if we're letting you use it, then use it. So the first step is the molar mass of find the molar mass of calcium chloride. So calcium carbonate. So what I got, and tell me if you guys agree, I've got 1 calcium at 40.08. I've got 1 carbon at 12.01, and I've got 3 oxygen at 16, and the total I got is 100.09, class consensus.
Yeah.
Yeah.
Okay, so then I'm gonna go 100.09 grams of calcium carbonate is equal to 1 mole of calcium carbonate. Grams cancels out. Now I'm in moles. Now that I'm in moles, I can relate the moles to count. So to count formula units, I have to use Avogadro's number. So I have 1, I'm going to use this equality now. So I have to put moles on the bottom because kitty corners cancel. So I'm going to go 1 mole of calcium carbonate is equal to 6.02 times 10 to the 23rd formula units of calcium carbonate. Moles cancels out. I'm left with formula units, which is what they're asking for. Now I just do my math. So I'm going to go 2.57 times 1, which I don't really have to do, times Avogadro's number, hit your equal sign, divided by 100.09. I want you guys to realize you could do this in any order. You could go 2.57 divided by 100.09, hit your equal sign, and then multiply by this. You could take this, divide it by that, and then multiply it by that. As long as the numbers on the top are being multiplied and the numbers on the bottom are being divided, you'll always get the right answer. So what I got was 1.55 times 10 to the 22nd formula units of calcium carbonate. Is that what you guys got?
Yeah.
So how come you have to put the 10 to the 22 after it?
Okay, because in your calculator, if you notice, probably in your calculator, depending on your calculator, it said something like 1.55 and then a whole bunch of numbers and then E 22. That E means times 10 to the. And I would say that's the most common mistake that kids make is this, because this is a really big number. If you just put 1.55, first of all, you can't have, like if I have a sample, 2.57 grams of calcium carbonate, there's not going to be 1.5 or formula units in that sample. There's going to be millions in there, billions, trillions. So if you see that E in your calculator, so if it showed up and you saw that E and then it went 22, you have to put in the times 10 to the 22nd. So the number that comes after the E is the exponent when you put it in scientific notation. Does that answer your question?
Yeah, the only thing is like mine says like E to the 24. I don't know how it doesn't say to the 22.
Okay, can you please hold up the calculator that you have for me so that I can see what version it is?
It's TI-84.
Okay, that's why. All right, so let me show you something. The easiest way, so you're not using the scientific notation button, so what's happening is that your calculator's reading the wrong order of operations. So I'm going to show you how to put it in using the scientific notation button.
Okay.
Okay, so can you see this right here?
Mm-hmm.
Okay, so on your calculator, so if I were to put this in scientific notation, I would go 6.02. Now, on this comma, do you see the EE above it?
Yeah.
That EE means times 10 to the.
Okay.
Use that button. So you'd go 6.02, hit your second, and then EE, and then just put in 23. What that does is it connects the coefficient, the 6.02, to the times 10 to the 23rd, and your calculator won't read the wrong order of operations. So that's the easiest way to do it, in my opinion. If you write it out, if you actually put in 6.02, then the times, then the 10, and then the caret, and then the 23, you have to put that whole thing in parentheses so that your calculator reads that as all like sticking together. Does that make sense?
Yeah.
Okay.
Thank you.
So did you figure that out? Are you good with that?
Yeah.
Okay. All right, good. Okay, so try it now and then see if you can get that answer.
Yeah, I got it.
Okay, beautiful. Okay. So that is it, my darlings. Do you have any other questions that you want me to talk about?
I don't think so, no.
Okay.
Yeah, no, I'm good.
Does that clear up any questions that you had?
Yeah.
Yes.
Okay, awesome. All right, so thank you for coming to see me. I get lonely sitting here in front of my computer all day, every day. It's like Groundhog Day. It's like, okay, I'm gonna go do this again. Okay, I'm gonna go do this again. So how are you feeling about content in general? Like, do you feel like it's fair? Is it taking you a relatively short period of time? We're shooting for about 2 hours per week. Is that what's happening?
Yeah, I don't think it's that bad.
Yeah.
Okay. All right, good. Okay. I'll be here, same place, same time next week, guys. Don't forget office hours on Friday from 11 to 2. Feel free to pop in and out as you please. I hope everyone has a good day.
You too.
Thank you.
Cool. Thank you.
Thank you.
Yep.
All right. Bye.
Bye, guys.